ppb, parts per billion, parts per million. Those are the measurements of concentrations there. So in this particular learning objective, we want to introduce one of the many measurements for the concentration, molarity. So you have to, it's a definition, you have to know how we define molarity, and then using molarity as our conversion factor to do stoichiometry problems involving aqueous solutions. When we try to do dilution, when we try to do titration, quantifying the amount of chemicals in a particular solution there, we can use molarity as our conversion factor. Okay, so solution, when we're dealing with solutions, how do we define, that's a D word, something that you need to pay attention to. You will be tested on the definition of the solution there. So a solution is a homogeneous mixture of two or more substances. Now when you look at the term solution, the first thing come to mind is liquid. The solution doesn't have to be liquid. We have solid solutions, we have liquid solutions, we also have gaseous solutions. Air is a perfect example. As long as you have two or more substances mixed together in a single phase, or homogeneous mixture, that's a solution. So air, you have 78% of nitrogen, 21% of oxygen, carbon dioxide, helium gas, or argon gas, and those trace amount of gases there. They're all mixed together. You can't tell which part is nitrogen, which part is oxygen. So it's a homogeneous mixture of two or more ingredients in there. So the components of the solution, by convention, we give them some different terms to describe what's in there. Okay, and solute is the one that dissolved in the solvent, and solvent is the medium in which a solute is dissolved to form a solution. So in aqueous solution, the solvent is always, in aqueous solution, the solvent is always I'll wait until you come up with the answer and spell it out. Water, thank you. So in aqueous solution, this solvent is always water. Everything else is dissolved in there. Okay. So when we introduce the concept of concentration there, one of the ways that we measure concentration is molarity. By definition, that's another D word. We run a lot of D words there today. And definition of molarity: number of moles of solute per liter of solution. Okay. So in order to calculate molarity, we need to know how many moles of solute, say sodium chloride dissolved in water, sugar dissolved in water. Okay, if we ask you to calculate the molarity, you have to know how many moles of sodium chloride or how many moles of sugar that we have. And then you dissolve in certain quantity of liquid and you come up with the total volume of the solution there. Total volume of solution has to be in liters. Okay, so moles per liter, that's how we define. That's how we define molarity. And this is something that you need to memorize. You need to know the definition. I guarantee you I'll put in a question in the, as one of the 25 questions in your second exam. How do you define molarity? I'll give you choices there. Pay attention to how we define molarity. Otherwise you're going to miss those 4 points there. So that's a free giveaway. 4 points already. You know what's going to be in there. I'll see how many people miss that question. How do we define molarity? Moles of solute per liter of solution. If you have a number representing the molarity, like 1.00, capital M is what we use to represent molarity. Okay? If you have 1.00 capital M of sodium chloride, C for concentration there, okay? That means for every liter of the solution, you have 1 mole of sodium chloride dissolved in there. Now, sodium chloride, sodium, chlorine, sodium is 21, chlorine 36, and you add up sodium is 23, and chlorine is 35.45 there. You add them together, you get 58 grams. So that means for every liter of the solution, you have 58 grams of sodium chloride dissolved in there. And that's what molarity is all about. Giving you the relative quantity of solute in moles per liter of the solution. Okay. Now, this is our new conversion factor. Okay. If you look at this particular definition there, if we give you the molarity Okay, that gives you the equivalency of the moles per liter of the solution. Now, if we give you, say, 26 liters of a particular solution, 26 liter multiplied by this quantity, liter and liter cancels out, and you can figure out how many moles of the solute dissolved in there. Or if we give you, say, 26 moles of a particular compound there, we ask you to dissolve them in 5 liters of water. Well, 26 moles divided by 5 liters, you end up with molarity there. Yeah, so this is the new conversion factor that we give you here. So the unit for the molarity is moles per liter. We will introduce later on in the semester, we will introduce other measurements for concentration, and you have to pay very close attention to the unit of this quantity here. It's moles per liter. That means if you get 1 liter of that solution, you get so many moles of the solute in there. You can convert that into grams based on mole amounts. So when you try to prepare, say, a 1.00 capital M moles per liter sodium chloride solution, all we need is to have 1 mole of sodium chloride, a solid, somewhere around 58 grams. Put it in a bottle, and we use what we call a volumetric flask. Now, in the volumetric flask there is always a mark somewhere on the neck of the bottle there. If you add liquid, so the liquid level or meniscus rests right on that mark, and you have exactly whatever volume is marked on the volumetric flask. And this is a 1 liter bottle, for example. If you put water right on that mark there, you have a total volume of 1 liter. Now you have 1 mole of sodium chloride dissolved into 1 liter of solution. You end up with 1.00 capital M moles per liter of sodium chloride solution. So that's how you prepare a particular solution for a given concentration there. Okay. Now, when you dissolve ionic compounds in water, something happens there. The ions becomes free ions, and the ions that used to be clustered together, attracted to one another in the solid state. Once you dissolve them in water, they can move freely, and you end up with free ions moving around. So one thing that you do need to pay attention to, if we ask you to calculate the ion concentration, the ion of each kind in an ionic compound dissolved in water, the ion concentration may or may not be the same as the concentration of the compound. So if you have, say, copper chloride, or I should say copper 2 chloride, with the Roman number there, that means copper has 2 positive charges there. Now, for every 1 copper 2 ion in solution, there will be 2 chloride ions in the solution. So we can measure the concentration of solution of copper 2 chloride. We can also measure the concentration by the ion itself. Now in this case, if you have, say, a 0.30 moles per liter copper chloride solution, then the copper concentration, copper ion concentration is 0.30 moles per liter. The chloride ion concentration is twice as much because of this molar ratio. So that's something that you do need to pay attention to whenever you have an ionic compound. How do you recognize ionic compound? Well, chapter 2, chapter 3, we talked about that. When you have metal, no metal, ionic compound, okay? When you have polyatomic ion, positive charge,